Hello, everyone. Welcome to today's webinar, Container Security Top 5, Kubernetes in the Wild. My name is Uday Shetty. I manage partner integration at Mirantis, and I'm pleased to moderate today's event for you. Security is the number one issue for enterprises, as data thefts, IP thefts, malware are causing enterprises huge loss monetarily and customer confidence. As customers begin their cloud journey by containerizing their apps to accelerate development cycle, faster time to market, security challenges remain a concern due to large attack surface area and requires better coordination between developers, operators, and security experts. So recent article from CNCF states 40 to 50% of enterprises have some security gaps. Today's session will cover best practices to assess and address security risk. So before we begin, I would like to address a few housekeeping details. First, recorded version of this webinar will be available on demand. It's on the same link. Your phone lines and your computer microphones will be muted throughout the presentations. You can ask questions on the question icon box on your right-hand side. And the live questions will be open after the presentations. With that, I will provide a brief introduction to our speakers. So without further delay, let me introduce our speakers today. Brian Langston, Senior Solution Architect, Mirantis. Brian has been with Mirantis for 6 years. During that time, he has led America's architecture team with Mirantis Services Division and has been a senior pre-sale solution engineer for the past year. Brian advises many of our large customers on methodologies related to security and compliance. He is also part of advisory council at Cal State University Chico's Cybersecurity for Executives program. David Belcher is an associate principal consultant at Synopsys. David is a 15-year veteran of cybersecurity industry. David has seen it all. He has worked on everything from deep technical vulnerability research to high-level architecture, design, and consultancies for top companies at governments around the globe. Over the last 6 years, David has had focus on emerging world of container technologies and is here to share his experiences. We're looking forward. Brian and David will share their experience working with customers on cloud native security challenges. With that, Brian, take it away.
All right, thank you, Uday. And thanks everyone for joining today. As one might look at this title slide and think of animals in this landscape coexisting in peace and harmony, somebody else might look at it and notice that there also exists a threat on some scale. In our discussion today, we want to address the threats that have emerged in the cloud native computing landscape that also might not be well known. So my name is Brian Langston, and I'm co-presenting today with David Belcher from Synopsys, as Uday mentioned. We both have significant experience working with companies on critical security challenges and methodologies. We've worked with many customers to design and implement methodologies that help identify and address container security risks. So our objectives for you in this discussion today, we want to help you understand various attack surfaces that can expose your application to the outside world. And with that objective in mind, we'll talk about our top 5 container security risks. We also want to highlight best practices to assess and address specific security risks prior to deployment in the enterprise. And then finally, we want to help you all understand how Mirantis Kubernetes Engine and Synopsys Security can help you mitigate these security risks. So David Belcher is going to get us started with container security risks. David?
Thank you, Brian. So, I mean, Ordinarily, if this was an in a face-to-face presentation, I'd be asking you, hey, so let's think about security risks when it comes to containers, and ask you to maybe suggest some. That's not going to work this time, but I'd like just to think about, when you think about container security, what do you think about? What are the key concerns that you're looking at? Now, if we look at this large diagram, I'm not going to expect you to read everything. This is our current view of the container security capability model. Now, the first thing and the primarily thing that a lot of people will talk about when they're talking about container security is that box on the top left. That's your container image security. Most customers we speak to, all of their effort in container security is put into that. That they're doing image scanning, that they're doing verification of those images. Hopefully, they're managing how they build, deploy, and store those images in registries. But that's just one small piece of the broader container security kind of landscape, if you will. And when we think about container security, we're thinking about everything from the ground up. So they include your infrastructure. It includes the engine itself. So how is the container runtime secured? Be that Docker, be that one of the plethora now of different engines that have popped up. Looking at the platform, so in this case, Mirantis Kubernetes engine, looking at how you're managing secrets and volumes. And then it goes all the way across to things like, how are you monitoring your containerized environment? Are you using container-aware audit tools? Are you putting in place a process to respond to container security incidents? So that's a pretty big arena of things to consider. So what are the top 5? I think that's the key message for this one. So here is a top 5 list of the things that we as consultants generally encounter when we're looking at containerized environments. As I mentioned, number 1 is around the image security piece. So this is more than just scanning your images. This is also looking at how are your development teams creating those images. So not just vulnerability scanning, but also are they adhering to policies and best practices when they create those images? Are they using minimal base images? Are they making sure they include a non-root user within that image? Are they making sure they're only installing the packages and libraries that they need for that application? How are they deploying it? Are they deploying it into a trusted registry? How are those images in that registry managed? And some of those things we'll be talking about when we talk about Mirantis Container Registry as well. So beyond the image security, as I said, that's one small piece. We're looking at secure defaults and hardening. So this is everything from securing the supply chain, so making sure that your management of that registry is solid and on point, but also hardening your deployment. If you're self-managing Kubernetes, are you configuring your kubelets correctly? Are you locking down your etcd? How are you managing role-based access, which we talk about later as well? And how are you kind of hardening that whole environment? Number 3, secrets management. So in general, if you have any kind of microservice architecture, there's going to be some secrets kicking around. That could be TLS certificates, could be credentials for various services, like SSH keys, databases. If there's databases, you're going to have credentials for those. So how are you managing those? Are you throwing them into a standard etcd, or are you using some third-party secrets management tool like Vault, or if you're in a managed environment, a managed key store? So that's actually a large piece, and securing those secrets is pretty important. Number 4 is around network segmentation and firewalling. So by default, within a Kubernetes environment, there's free and open communication between everything. That's necessary because by default, Kubernetes or any cluster is designed to work for the vast majority of cases. So everything's default wide open. But when you come into looking at a multi-tiered microservice or multi-tenant environment, where you have higher risk application containers, application pods, and then more secure or items that require more security, such as management plane items, data plane items, and other orchestration pieces. How are you separating those? Are you ensuring that internal APIs cannot be leveraged by pods or containers that don't need that access? So ensuring that we understand the complexities of that network segmentation and applying it at the cluster level. And then finally, the policy enforcement. So we've discussed lots of things. We've maybe had an architectural discussion with you and highlighted lots of risk areas. Maybe we've performed assessments and we've found certain vulnerabilities or weaknesses or misconfigurations. How then do you go about and ensure that those things have been applied at scale, and they're able to scale with the ever-changing size and complexity of your infrastructure? And that's where it comes down to policy enforcement. So helping understand how to do so. Now, when we move on to when we're talking about managed Kubernetes, so MKE, EKS, or any of these platforms where you delegate some of the responsibility of the security of the platform to that platform owner, there are also additional configurations. So the shared responsibility model is always the first consideration because you are ceding control of the control plane to that managed partner. So understanding where that delineation is, what they provide, what you need to do with them to help secure your cluster, and then what's your responsibility for the applications running on top. Looking at the network policies is another piece, as I mentioned in the previous slide. So ensuring you put in place security policies that secure the applications running in the cluster. And this goes layers on top of the infrastructure piece itself. And then looking at your security policies themselves. So PSB, although pod security policy has been deprecated now, but looking at other tools like OPA, Gatekeeper, looking at other tools that are available to enforce policy, things like SNCC has something, Prisma Cloud Compute, and all these various tools you can put in place to enforce those policies and to ensure that images are scanned before they're deployed to the cluster, make sure you have runtime monitoring, and able to detect those hard to see issues that are hiding away within those containers. Looking at your image registries. So how do you store and deploy images into your cluster in a managed environment? A lot of managed environments, including MKE, do have secure registry options, and that'll be discussed more later. And then also looking at like data and secret storage. That is often outside of the managed Kubernetes environment, although they will provide options, and then it's down to making a decision around what's the best option for you. Do you run multi-cluster? Do you want to have an external secrets management, or do you want to use whatever's available for the specific managed platform that you're working with? So this is some high-level considerations, but what does this actually look like in the real world? So I wanted to throw in some stats here just to give you an indication that we know this is a hard problem, that everyone has challenges, and the ever changing dynamic and complex nature of building out microservices and container-based architectures lends itself to problems if you haven't taken the steps to understand the risks and define how to manage and deploy those architectures. So as we see from here, that in 2020, StatRox, well, every year StatRox do a survey of Kubernetes users. And then in the 2020 report, 90% of the survey responders mentioned that they experienced some form of Kubernetes security incident. Of that 90%, around 67% were due to misconfigurations. So this is where they've some things open to the internet shouldn't be. Maybe they haven't hardened some part of their Kubernetes environment. Maybe they're deploying pods in an insecure or dangerous way. So some form of misconfiguration issue is the vast majority of these problems, and all of this can be addressed by having solid policies in place. 17% runtime incidents. So these are more akin to like direct attacks against applications or services running within the cluster. And 16% are compliance audit failures. So if you have specific compliance requirements, ensuring that your cluster is configured to adhere to those is important. And of those, I just wanted to throw out a few of the kind of high profile incidents that we've seen. So Capital One was probably one of the earliest and most publicized issues. The Capital One issue was a misconfiguration abuse. So they had some network policy issues which allowed the access to internal metadata APIs. That was leveraged to get to gain deeper access to the cluster, and the result was around 30 gigabytes of credit application data was stolen. which has affected around 106 million users. So Docker Hub. So this allows us to talk about supply chain. There was an issue where many images across Docker Hub were compromised. Now, these weren't the Docker official images. There were other images on Docker Hub, but there was a general problem a few years ago where people generally trust things coming from Docker Hub, regardless of who put it there. And just like GitHub, anyone could put images into Docker Hub. And we saw a whole swathe of images that were modified or just malicious images put up there, which contained cryptojacking software. Cryptojacking, for those who aren't aware, is just a small process which performs Bitcoin mining and does it within your cluster. And in doing so, exhausts your resources or uses your resources, which can get quite expensive in the cloud environment, to mine Bitcoin and earn money that way. Tesla, in the same way, they were compromised via a exposed admin interface that was unauthenticated, and that was leveraged to deploy pods into the cluster, which performed crypto mining attacks. And these were particularly interesting because the attackers, they tuned the crypto mining processes to make them much harder to detect. So low and slow over a longer period of time. And the recent one is the Hildegard malware. Some may have heard of that. It was reported January this year. Now, this is a malware which basically spreads across the internet looking for clusters with misconfigured kubelets. The kubelet, for anyone who isn't aware, is a small agent that runs on every node within the Kubernetes cluster and is how the cluster communicates with all the various components. Misconfigured kubelet, by default, the kubelet is unauthenticated, and if that's exposed to the internet, an attacker can leverage that to be able to deploy workloads into your cluster. And this is being exploited by the Hildegard malware. So hopefully that gives you a good high-level understanding of the general risk environment we're looking at. So I'm going to pass it back to Brian, who's going to speak a little bit about Mirantis Kubernetes Engine and some of the things that they're doing to help protect us against a few of these issues we're seeing.
Yes, and so true. Yeah, just this week, I think we've all maybe heard of the meatpacking facilities that were hacked, similar to the East Coast pipeline recently. So yeah, there's no shortage of incidents, unfortunately. But also, unfortunately, there isn't any one thing to do or implement that will prevent your own organization from becoming a victim of such an attack. As David's slide mentioned a couple slides ago around the complexity of security, but there's a lot of industry best practices and products that, when implemented with a well-defined security policy, can at least help reduce your own attack surfaces. So DevSecOps first is a term that refers to the continuous delivery of security processes within your software development framework. It's kind of a summary definition that I have. A secure software supply chain is what we refer to within Mirantis as the set of integrated people, processes, and technology that produce and deploy your container applications. All right, it's a software factory. So this slide outlines what those relationships are at a really high level and how they're connected. Now, going over every aspect of security within a secure software supply chain takes a lot of time. So for purposes of this discussion, I want to focus on two key pieces that are in the center of the slide, and that's Mirantis Kubernetes Engine and Secure Registry. So Mirantis Kubernetes Engine is focused on ensuring that your containers deploy and run securely. So Mirantis Kubernetes Engine follows a secure by default approach to addressing security problems. And what we mean by secure by default is really represented in three key areas of container security. And the first is access. Mirantis Kubernetes Engine provides RBAC on top of Kubernetes to support the principle of least privilege. That's a common security concept within Kubernetes security and others. But in addition to RBAC, though, Mirantis Kubernetes Engine employs several other security concepts and features such as SecComp, AppArmor, SE Linux, all designed to restrict access to syscalls by a given process. There's pod security policies for protecting cluster level resources, network security policy for isolating pods from a network level, and many others, right? I'm just highlighting a few. Secure by default from a content perspective, I'll cover in the built-in content trust. But when we talk about platform secure by default, Mirantis Kubernetes engine is part of Mirantis's broader cloud native platform. And when building a secure by default platform, it's important to consider governmental use, right? Other use cases where the security requirements are even more restricted and more defined. So in coordination with the Defense Information Systems Agency, or DISA, Mirantis has produced a STIG, which is a security technical implementation guide for our cloud native platform. So a STIG is basically an extensive checklist describing what a secure implementation looks like. And having a STIG allows government agencies to ensure they're running their platform in the most secure manner. So this is a very powerful concept that helps us work with our customers and provide them the platform that offers them the protection that they need. So together, these are three very powerful security concepts. Regarding FIPS 140-2 encryption, Mirantis was the first in the industry to provide that level of encryption. And for those who aren't aware of what FIPS is, that's the Federal Information Processing Standards, which is itself just a set of publications that are developed and maintained by NIST, which is the National Institute of Standards and Technology. Sorry for all the long terminology, but when you get into security, there's a lot of acronyms and long government agencies that are involved. So NIST is a US federal agency, but the essence of FIPS is they define the security, they define the security criteria required for government computers and telecommunication systems. And the 140-2 part of FIPS specifies how cryptographic modules are used to protect your sensitive but unclassified information. So FIPS 140-2 is super, super critical for those workloads that require encryption at a very in a very secure manner. And then content trust. Content trust is the cryptographic guarantee that the image pulled is the correct image, right? It provides the ability to verify both the integrity and the publisher of all data received from a registry over any channel, even in secure channels like the internet. So in practice, built-in content trust provides improperly signed or unsigned container workloads from running in your environment. There's much more that can be said and described about Mirantis Kubernetes Engine security. It's available on our website, but I also wanted to touch on the Mirantis Secure Registry part of our platform, which is focused on the inputs that get deployed to your production environment. And again, this is not a comprehensive list by any means, but touching on some of the key parts of Secure Registry as it relates to you taking quick and easy steps towards securing your container deployments. So the first is image scanning. This is an optional feature that allows you to scan images at the binary level and then correlate those findings against a regularly updated CVE vulnerability database. And this is something that everybody should be doing. The concept behind image signing is that you can digitally sign and verify image content and the image publisher. So within a pipeline, and again, we could refer back to the secure supply chain and whatever implementation of a pipeline you have, within that pipeline, your downstream users and automation tools can verify authenticity before running in production. And then the next item is policy-based image promotion, which is about providing your organization with the right automation framework to create a policy that says, for example, that an image can't be run in production if it hasn't been scanned in more than 30 days, right? Those and many other kinds of policy-based image promotion, or just those policies can be defined to help regulate and govern how your container applications and images progress through that pipeline. But it's not just about predefined policies, but the ability to create custom policies. So Mirantis Secure Registry supports the creation of custom policies that should be written to help enforce any additional extra and custom requirements that your organization might have. So there are multiple sources of container security best practices within the industry. NIST 800-190, for those that aren't aware, that's basically a publication that outlines best practices and requirements for container environments specifically. There's lots of other NIST publications for general IT, but NIST 800-190 is geared towards container environments. So I would highly recommend becoming familiar with what some of the methodologies and requirements and best practices are that are outlined in that publication. Earlier this year, FedRAMP published 6 container vulnerability scanning requirements that are actually mandated for all FedRAMP implementations. And in fact, those 6 requirements must be implemented by September of 2021 to have a plan for that. So by itself, out of the box, Mirantis Secure Registry supports these 6 requirements and other best practices out of the box. The broader Mirantis Cloud Native platform, of which these 2 products are a part, Mirantis Kubernetes Engine and Secure Registry, they satisfy a significant subset of the requirements outlined in that NIST and FedRAMP documents I just mentioned, all out of the box. Now, I call out these 2 sources of information for a reason. Your company's compliance team has to see evidence of performance against some kind of methodology that enforces the requirements from these publications and any others that make up your organization's compliance framework. So David is going to outline methodologies that his company has developed and refined through repeated customer engagements.
Great, thank you, Brian. So as I was putting together this deck, I didn't want it to make it all kind of pretty infographics of these great offerings we have and turn it into a sales pitch. What I really wanted to do was to help you really understand the intricacies when it comes to assessing container architectures and really go into some detail. So I apologize for those who are less technically minded. Please feel free to ask questions and I'll clarify during the questions section anything I go over, but I really want to give you a kind of a window into how we approach the assessment and securing of containerized workloads. So this is our kind of high level view of the key pillars of our security activities. Obviously, everything is underpinned by training and awareness, of which webinars like this is a key aspect, helping our customers understand the risks that are inherent with containerized environments, understand the approaches and tools and other activities that need to take place to ensure that their business risks are addressed and to make sure that they're adhering to all of the best practices and secure approaches to deploying microservice-based architectures. Beyond that, our key pillars are, first of all, architecture reviews. And I'm going to go into each of these in detail over the next few slides. But from a high level, architecturally. So shifting as far left as possible, helping you understand as you design and architect environments, the key risks, looking at your designed architectures, finding out what those risks are, and helping you understand at a high level any changes or any other adaptations needed to address your business risks. Technical security standards piece, which is helping our customers develop those policy documents, which will drive how they deploy and manage those environments. A container vulnerability assessment and penetration testing. Those are the more technical hands-on testing pieces, and I'll go more into those over the next deck. So first, let's talk about kind of architectural piece. Now, I just wanted to go talk at a high level here because this is a pretty deep and nebulous topic, as I'm sure you can appreciate. When we're looking at architecture reviews, we'll generally look at it from multiple different aspects. So we have threat models and architecture risk assessments, and those are essentially where we're diving deeply into a designed architecture. We're identifying all of the threat actors, all of the data assets within the environment, all of the threats that are associated with those, and all the security controls you have in place, identifying any gaps that might exist, and ensuring that we provide some recommendations on how to fill those gaps. With the ARA aspect, adding in a manual verification of all those risks we find. But also this includes those early conversations. So if you're considering doing something and you want to know what the risks and pitfalls are, this is generally where we have that conversation. But specifically, so let's say we're looking at the various components of a Mirantis cloud native platform. What are the sort of things we're going to be asking? What do those conversations look like? So through discovery, we want to make sure we understand what technologies you're using. So when we're looking at something like, let's say the Mirantis Kubernetes itself, we'll be asking you, okay, so how are you using Mirantis Kubernetes engine? Do you have multi-tenancy concerns? Are you having multiple different environments within your cluster? Do you have developers deploying custom code into those environments? Do you have customers interacting with various different pieces? We're talking at what services are exposed. So what's your web front end look like? What APIs are you exposing? How are you managing your role-based access? So who can access the cluster? Who can access various components? How are you limiting that access? How are you managing your secrets? So, and what secrets are there? Are you doing TLS everywhere? So how are you managing those TLS certificates? So many questions to help us really understand the context deeply. And highlight those areas where there can be additional steps taken to improve the defense in depth. Because we're looking at particular threats when you're looking at a containerized architecture that you wouldn't see in a traditional environment. With the additional complexities. And also, by default, for example, if a container is compromised, you're looking at internal network attacks, you're looking at container escapes. And if you escape from the container, that's potentially going to be as a root user. So there's the additional threat landscape. So really helping the customers understand the intricacies and additional attack surface that come with containers, and understand that context so we can really provide some good guidance there. So once we've had the conversation around the architecture, and we want to really get into a deep analysis, this is where the container vulnerability analysis comes in. So generally, it's a 4-phase process, although the first 2 and the second 2 generally will happen concurrently. The discovery phase. So the first thing you need to do when you're looking at a vulnerability analysis of a Kubernetes cluster or any other containerized architecture is really understand the context. And any of my customers will know that the key phrase I use is context is key. There's not generally one specific way you can deploy a cluster and assume you're good. There's no example of, okay, so this is a microservice architecture that you can pick up, drop into your environment, and you're good to go. There's always going to be nuance. Like I say, so the multi-tenancy questions. Are you running arbitrary code? How are your containers deployed? What containers are being deployed in there? There's lots of context we need to set. So we have those initial conversations. If we've already done a threat model, we'll use that information as well to really define the key assumptions and assertions. So when I say assumptions, I mean things like, okay, so we assume that this piece of technology we're using provides us this security functionality. So we assume, for example, that the Mirantis Secure Registry is protecting our images. And then we have assertions. So assertions are saying we assert that tenant A cannot communicate or interact with tenant B in any way. That there's no way to that a user through the web front end can access data from a different user. So these assumptions, assertions define business risks, but also the aspects that we need to verify for them. We also we highlight the key risks, so business risks and technical risks, and the key threats to that environment, and use that as a benchmark to then do the analysis and attack phase. So once we have all the information defined, we then move into the analysis and attack phase. Analysis is where we're doing a deep configuration analysis. So we're leveraging the Kubernetes APIs. We're looking at your managed platform configurations. We're taking a view of the environment. We're marrying that up to the expected view of the environment, making sure there's no discrepancies. And then we're taking those assumptions, assertions, and key risks, and we're verifying against those. So if your assumption that you have a certain functionality from something has been stated, we will verify that you're getting what you're expecting. If there's an assertion, we're making sure that the configurations are set up to correctly meet that assertion. And then the attack phase is the manual assessment. So this was essentially is the container pen test, which I'll talk about in a minute. And here we're actually manually verifying that, okay, so we've seen this configuration weakness, we're verifying that's actually a problem. But beyond that, this is also looking at the applications, the services that are running inside the cluster, and making sure that we are assessing and testing all of those pieces. Now, this assessment generally, there's various different aspects we need to look at. So if we move on to the next slide, and I'm going to talk more about the container penetration test itself. But there's 4 key scenarios that we consider when we're looking at attacks against the containerized architecture. The first 2 are pretty standard network penetration testing. So the malicious entering the public network, so this is outside the cluster. We're looking to see if there's any services exposed which shouldn't be, or any services exposed that are subject to attack. So this would be if you're exposing a web service or APIs, there'll be attacks against those. If you are inadvertently exposing an admin interface, like in the Tesla breach, we detect those as well. And making sure that there's no external threat actor who can compromise your cluster. The adjacent network is similar and is more akin to an internal network pen test. So this is partly covered by the malicious application container. So if a container can attack the network internally, but also if you're deploying this into a corporate environment, have you set up perimeter controls such that an employee or a malicious employee on that corporate network, ensuring that they can't then compromise that cluster themselves. Scenario 3 is a particularly interesting one that we actually see a fair amount of. And this is where you have some insider or developer or ops person who has some restricted access to the cluster. Let's say you give them access to the Kubernetes API to be able to access logs or audit information or do some kind of limited function within that cluster. These attacks are where we would verify, okay, so you're giving them a limited access. Are they able to escalate that access within the cluster? Is the access you're giving them limited enough? Or if it's a malicious developer, maybe we'll see if we can deploy a malicious container into the cluster using their level of access, and then from that pivot and exploit that cluster access to again escalate privileges within the cluster, attack other services, and perform other malicious behavior. And that's particularly important where you do have environments where you expect your team to be deploying into that cluster. Number 4 is the bread and butter of the container pen test piece. So this is, there's 2 key things we're looking at here. One is malicious containers. So this is where you're not using a trusted registry and an image being compromised, or you haven't set up your policies to prevent people deploying images from external registries like Docker Hub, or some supply chain attack, as we've seen with things like SolarWinds, where images are compromised in the registry and malicious code has been added. So we're looking at malicious containers, but also compromised applications. So this is scenarios where, let's say you have a web application front end. There was a vulnerability in that web application that an attacker was able to leverage to gain a foothold inside the container. Either way, we consider the attack vector that there is an attacker who is resident in a container inside your cluster. And a lot of the defense in depth that Brian talked about around setting up the app armor profile, setting up the other container hardening, is to ensure that isolation. So we are testing that isolation. We're looking at like 5, well, actually more than 5, but generally 5 key things. We're looking at containers of the host. Can we break out of that container in some way? Have I managed to gain execution in a privileged container and I'm able to mount the host volumes of the node? Or am I able to leverage like other weaknesses in the configuration to break out the container and gain access to that node? Container to network, as I mentioned with the JSON network, is from that container, can I access APIs and services within the cluster that aren't exposed to the internet and that maybe aren't as configured as securely as they should be? So can I leverage, let's say, your etcd because it's not secured? Can I leverage an internal backend API that doesn't have authentication? Can I attack a misconfigured kubelet? Like we saw in the, well, as I mentioned, in that malware that's been released this year. Container to container, we're looking at 2 kind of scenarios. So networking, by default, all containers within your cluster have a container network, which is kind of like an overlay network, where they can communicate with each other. So can we attack other containers through that overlay network? But also looking at volumes. So let's say you're sharing a data volume between 2 containers that contain some data. Maybe those volumes are read-write. And maybe a malicious container can modify the contents of that volume, which is then picked up by an alternate container and maybe changes the way it runs. Maybe change the configuration, maybe changing the certificates. If you've shared the CA certificates into a container, maybe the attack will modify those. But doing something to either network or through volumes that's going to affect other containers in the cluster. Namespace to namespace is typically looking at that tenancy conversation I mentioned a few times now. So if you require, as part of your business risk strategy, that tenant A should not be able to interact with tenant B, we'll perform multiple different attacks and approaches to try and bypass those restrictions and hop from one namespace into another namespace. And the final one's a bit of an edge case. So cluster to cluster. This is for those scenarios where you have multiple Kubernetes clusters, but maybe you've shared something between them, shared credentials, shared CAs and certificate trust, such that if we compromise one cluster, we can gain the information we need to then be able to pivot and attack some other cluster. And in some cases, it also includes cluster to other services. We actually saw one customer who included in the secrets of their Kubernetes cluster the credentials for their VMware virtualization farm, such that we are able to pivot access exploitation of the cluster to actually gaining full admin access to their entire vSphere infrastructure. So looking at those kind of attacks as well. So if we move on, and I mentioned that Kubernetes compromise container testing. Now I'm going to go a little bit into detail here. I don't want to see everyone's eyes glazing over for those who aren't super technical. I just wanted to give you a bit more of an understanding of what the container penetration testing includes, because it's somewhat larger in scale than a standard, say, a web application pen test or a network pen test, because often it includes many aspects of those. And so the container penetration testing, and this we actually do as a standalone as well. It's more of a black box testing, which includes these things, but also as part of the CVA. Now, if we were approaching this as a black box penetration test of a container, we'd have our deployed malicious container, and also with kubectl exec into specific application containers to perform an analysis. So we start off doing an internal pod analysis. So this is really seeing how we can live off the land within a container. We'd be looking at the environment variables, because in a lot of cases, secrets and configuration information is passed into the container through environment variables. So we'd see what we have available there. Looking at application configurations and secrets, are there things we can use to pivot to some of the services inside the cluster? Looking at what service accounts are in use. So if we're in a container and it has a service account that isn't a default service account that maybe has some additional privileges, how can we leverage that? And again, as I mentioned earlier, mounted volumes. So are there volumes mounted that we can interact with, that maybe more information's mounted than needs to be, so we can get information that allows us to pivot. Or maybe there's a volume that is read-write, and we're able to actually modify that content to affect the cluster. So doing a lot of internal pod analysis, we then move on to kind of container escape attacks, as I mentioned. So via host mounts, or if they've mounted the Docker socket in, or the cryo socket in into the container, maybe we can leverage that to escape. But looking at container escape attacks, we then perform network packet analysis. So here we'll do network sniffing to really see all the traffic running around inside the cluster. Because often there's a lot of traffic flying around, and because of the whole Fort Knox, my perimeter is so strong, I don't need security internally issue, often TLS is not enabled inside the cluster, and we can see communication between services that oftentimes includes credentials that we can use to then leverage those services ourselves, or other sensitive data. And then if there's custom protocols, we'd try and detect those, and then see if we can kind of leverage those issues, any issues with those protocols. And then network scanning, so internal kind of scan sweeps, see what services are available, all the Kubernetes services, but also the application services, enumerate those, figure out what's running, and try and kind of gain a good understanding of the internal workings of the cluster. And then finally, container service attacks. So once we have that list of things that are running, start doing attacks. Do API assessments to see if we can compromise an API. Maybe we've got the credentials or tokens needed to access the API via the network analysis, and then seeing if we can compromise that API service. Or maybe there's APIs and services that don't have authentication. Or maybe there's credentials we found in some configuration files, and we can use that to access a database, and from that database gain information. So maybe you're running a database that holds all the information for the cluster, and that isn't segmented, so we can pivot that way. So essentially looking at ways to pivot between services, but also to escalate within the cluster itself. So that's a lot, but it just gives you an understanding of the breadth and complexity of what we're looking at in the container pen test. And then finally, I just want to wrap up and talk about the technical security standards piece. So if we move on. So we've done architecture. We've helped you understand your key risks and concerns. We've done a technical analysis. We found the issues and configuration weaknesses that you have inherent. How do you document a standard for that? How do you document a words are failing me today. But how do we make sure that we can scale? You can scale up and make sure that these issues don't happen again. And this is where technical security standards come in. So here we're defining some baseline standards and technical implementations along with those standards to give you that roadmap and to give you that guide that you can give to your development teams and to your ops teams to ensure that a minimum set of security standards are put in place. They're very environment and technology specific. So each environment, so production versus not production, and each technology. So it could be a standard Kubernetes, could be an MKE, could be an OpenShift, whatever. They need to be specific because you're looking at specific configurations. And also project specific. So each project has some nuance, and you need to make sure that the security standard fits that product. And we'll generally look at two key categories. So required is for everything that must be applied, supplemental for everything that should be where possible, but strongly recommended. And for anywhere where you have a required policy, but that policy cannot be implemented for technical reasons, first of all, that should be picked up while you develop the standards. So as you develop these standards, that should be verified against with the development teams to make sure that all these standards are practical and applicable. Because, I mean, if we were to just say, apply all the CS benchmark standards, for example, if you applied every CS benchmark, the cluster probably wouldn't run. So making sure that these are practical is important. But where there is a non-technical reason why something can't be implemented, then definitely have in place an exceptions process where someone takes ownership of that risk, and there's a finite duration where that risk can be addressed, and then reassess that point. And just on the right, just to give an example of what one of those looks like. So this is a pretty mundane one. So enable LDAP as a required classification, and then provide some rationale and the specific settings. And here are the two ways to do so in Mirantis, Kubernetes engine. But having strong policies and standards is important because it gives you that kind of watermark. And the final important thing to say about the technical security standards is they should always be living documents. They should always adapt and grow and evolve with your environment as you take new risks, put in place new policies, as new technologies come into play. Make sure they're addressed and added as well, but use this as the guiding star for making sure that you are addressing everything you can when it comes to the security of a cluster. So that's me. So I'm going to pass it back to Brian for a wrap up.
All right. So as we've pointed out with examples of recent attacks that have occurred, with many of the leading brands that we're all familiar with, it's pretty clear that the level of sophistication in these attacks is pretty significant. And Kubernetes security is complicated. There's no question about it. There's a lot to enable. There's a lot to take into consideration, as David has pointed out. Different patterns and flows that need to be assessed to make sure that what's running in your environment is what you intend. So security is not just a matter of implementing security settings, and nor is it just running health checks. Health checks can only tell you whether a certain setting is in place, but what the impact of certain settings and allowances and grants and other concepts within Kubernetes security, running health checks itself is not sufficient either. While those are important to an organization's security strategy, again, the level of sophistication in today's cybersecurity attacks really requires a comprehensive approach to container security that includes some of the methodologies that we've outlined today. Accessing your containers, the content that's in the containers and the platform itself all need to be secure by default. And ideally, your container platform would allow for each of those areas to be configurable according to your own requirements and use cases. In addition, development teams need to look at their software processes like a supply chain with many gates and defined segments that allow for frequent and continuous measuring and assessment. If you break down your supply chain into these gates and segments that I'm talking about, it allows you to do more than just the frequent and continuous measuring and assessments. It really gives you the ability to define, smaller blast radiuses, right? And in security, that's a term that we use to describe and quantify what the kind of impact is if a certain attack surface should be exploited, right? How far can they get? How much damage can they do? How much change could they bring into the environment? So defining your pipeline into many gates accomplishes those objectives and allows for even greater transparency and accountability into the owners of those various processes, and then all automated with DevSecOps and DevSecOps and DevOps methodologies. So your assessment methodologies, as David has mentioned today, must account for various attack scenarios at multiple points throughout that supply chain. And then finally, we've, both Mirantis and Synopsys, we've helped organizations of all sizes and across all organizations with customers that are in various phases of their journey to a cloud native system, and helping them adapt to the various requirements that they have for their use cases, requirements, compliance frameworks, etc. So that's what we wanted to share. If there's any questions, we can spend some time addressing those.
Great, great presentation, and wish we had more time, but now we are open for questions. Do we have any? Yeah. David had a question about, you mentioned FedRAMP. How often it's published, and where do someone find more information?
Yeah, so that's an important one to keep up with. FedRAMP does have a website where they publish all of these different requirements and mandates, like the one from March of this year. You could go to fedramp.gov for more information there.
Right, thanks. Any questions from audience? David, in your slide, you mentioned a container pen test. Then you also have CVA. How do we have to use both, or is it pen test covers everything?
Actually, it's the other way around. So CVA covers everything.
Okay.
Essentially, you can consider the standard container pen test as more of a black box approach. So this is akin to like a standard web application pen test, where we select one or more of those scenarios that I discussed, and then from a black box standpoint, we perform analysis and attacks, as I mentioned through that container pen test slide. With the CVA, that's more of a white box assessment. So we're looking at the configuration of the cluster. We're doing a deep configuration analysis of the underlying components. And then with that information, we're highlighting those potential risk areas. And then we're performing the penetration testing activities to look at more of the application side, but also to verify those things we found. So the CVA is obviously a slightly more involved process, and it takes longer, but it gives you that much deeper full stack view of any risks and a defense in depth standpoint, whereas the pen test is more of a what's our immediate risk, what are the highest risk problems, and what's the specific attack scenarios we're likely to encounter.
Great, thanks. Do we have any questions from audience? Yeah, David, you also mentioned about, we talked about AppArmor, Sec Linux. It's very Linux oriented. Are these applicable to Windows? What are the things about, customers have a lot of Windows system, and we have containers, Windows supported on Kubernetes. Mm-hmm. What are the difference?
There's actually quite a lot of differences. So technically, there's a lot of similarities in the way that the Windows containers interact with the underlying subsystems. There were some parity pieces developed for Windows containers, but on the whole, there's a lot of differences. As you mentioned, a lot of technologies used to secure and harden containers are Linux-based. And they're designed such. I mean, even if you're running Docker on Mac, it runs within a virtualization of Linux. When it comes to Windows containers, there are other similar technologies in place. However, it should be noted that there is a significantly more complexity involved when you're doing Windows isolation. And in general, Microsoft do not consider container escapes to be a security issue. They have no intent to service when it comes to, for example, in Azure and in Google Kubernetes engine, so AKS and GKE. If you're deploying into Windows containers, which run on top of Windows nodes, Microsoft provides no guarantee of isolation because of the complexities involved. And have no intent to fix those issues. So their recommendation from Microsoft is that you do not use Windows containers in any situations where there's kind of multi-tenancy, so where there's that requirement for isolation, but also where you're intending to run untrusted third-party code. Because compromise of a Windows container cannot guarantee the level of isolation that you would have in a standard Linux container. So that's a key consideration there.
Great. Yeah, I think you brought up a great point. So David, when we talk about, Brian, when we talk about hardening FIPS, you mentioned on Linux. So since David brought up a good point about security, is this available on Windows as well?
Yes, FIPS is available, yes, as a configurable option for both Linux and Windows hosts.
So looks like we're running out. One more last question, David. We heard a lot about zero trust nowadays. Every presentation has zero trust. What exactly, is zero trust?
Yeah, I can speak to this, or Brian can. Essentially, zero trust is the idea that you explicitly deny access to everything. Zero trust is a situation where, let's say, you have a microservice architecture and you have multiple components. The traditional viewpoint is that these are all parts of the same system, so they inherently trust each other. Zero trust is a counter concept whereby you assume that everything inside your environment could be malicious, therefore you trust nothing, and perform that verification of those components as they interact with each other. Brian, do you want to go into more detail there?
Yeah, just to add to that, it really requires a very careful inspection of, as you mentioned, everything that you do, everything that you expose. Or want to expose. But again, starting, like you said, trusting nothing, and then defining everything via policies, grants, and other constructs within Kubernetes that provides for the exposing of different resources, which basically means your container platform has to expose those mechanisms. But just configuring them, in our experience, is not sufficient, because you still should be, and this is one of the main points in this webinar here, you still need to implement the right methodologies to kind of simulate the flows that you're trying to limit in this zero trust concept, if that makes sense. So have the right platform, have the right methodologies that assesses the effectiveness of the various security implementations that you're intending to do.
Right. Yeah, let's take one last question before we wrap up. You mentioned CIS benchmark. If I run CIS benchmark, is my cluster secure, or do we need to run additional tests?
Yeah, so I mentioned CS benchmarks earlier. So it's a yes and no answer. Yes, in a way, because in most cases, if you apply everything single CS benchmark, the cluster will not run. So essentially, if it's not running, no one can attack it. So that's great. But in generally, no. Because CS benchmark generally will cover a lot of the platform pieces. So you can secure the infrastructure. You can harden everything. You can kind of isolate your containers in the correct way. You can apply every CS benchmark, which secures the infrastructure and the platform, but that's only half the story, or even less than half the story in many cases. We also need to take into consideration the architecture of the microservices themselves. What internal APIs you're exposing, how the services interact, what public services you're exposing, how are you managing your role-based access to the cluster, how are you managing access to those services, how are you managing secrets between those services, what additional network segmentation they're putting in place, because that doesn't fall within CS benchmarks. So there's a whole kind of a layer of the application that CS benchmarks just cannot apply to that. So an example being an automobile. You could do every safety and security upgrade to your car. It can have ABS, you can have central locking, you can have all those things. But if you drive it like a hooligan, you might crash and die. So understanding that there is that separation there, and that you've still a lot to consider beyond just a benchmark recommendation.
Right.
Yeah, to add to that, sometimes there are good reasons for not implementing a certain line item within a benchmark, and got to remember it's just a set of best practices. Not to say that they should be disregarded or taken lightly, But in all cases, not every implementation of Kubernetes is going to be able to, as you mentioned, to be able to function properly. So you might have very valid reasons for not implementing a line item. And in those cases, I would just suggest documenting that and understanding what the mitigating counter actions that you have to take in order to avoid the risk that that line item in the benchmark is intended to prevent. So that's important to cover your bases still if you're not going to implement everything.
Yeah,
Right.
exactly.
Hope we answered all the users' audience question. Again, thanks to our speakers, Brian and David, fantastic job. Also, I'd like to thank everyone for coming today. Thank you.
All right, bye everybody.
Thanks, everyone.